So yes, I want to talk about AI evaluation, especially in the context of MR imaging. So as it's a good practice, I'll first start by stating my conflicts of interest. I'm a co-founder and shareholder of Varoquax. It was really founded by my friend and former colleague Pierre Fillard, and you should check them out. They do really cool things. This is from their website, Mammo Screen. You know, if you look at the website, it does lots of really good things. It does image assessment, informed score. It reduces fatigue. It's really nice. You should use it. It's cool. The team is nice. They're my friends, and maybe you'll make me rich. And anyhow, as you all know, radiologists are obsolete. It was announced in 2017. Okay. Well, the problem is if we take a step back and we look at the evidence, there is a big mismatch between the claims and the evidence. This is a publication from biostatisticians a few years ago that showed that during COVID, there were many publications on machine learning for COVID detection, but they simply did not have any potential clinical use. So yes, this is what I want to be talking about today. I want to be talking about the different challenges to medical AI evaluation. And let me start by the validation noise. So the problem is really simple. The way we test machine learning for medical imaging or machine learning in general is that we have a predictor that we have learned on a train set. It doesn't really matter how the predictor has been built. And we test it on a test set. And suppose the test set has 1,000 images, and I'm talking about a test set, so that's a pretty big test set by medical imaging standards. What I'm showing on the screen is the distribution of measured prediction accuracy, well, the error of the distribution, the distribution of the error of measured prediction accuracy on the test set. And the reason we have such a distribution is that each time we have an image, we have a certain chance of getting it right, a certain chance of getting it wrong. And so each time it's a bit like, you know, rolling a dice. You know, you might get it right, you might get it wrong. And you're rolling the dice and you're averaging the dice that you roll to find the average expectancy of the dice. And well, the problem is that, you know, I said rolling a dice, but I should have said flipping a coin because you only can get it right or wrong. So each time you get one bit of information. And given that each time you get one bit of information, well, it's a noisy measure. Okay, so if we look at how it's done in real life, this is an analysis of all the publications in the MICAI 2023 edition that do prediction from images in general. So each dot is a publication, and we're showing two things. We're showing the size of the test set on the x-axis, and the difference in accuracy between the best predictor and the second best predictor on the y-axis. And the color map is green when there is clearly enough data given the difference in accuracy to establish a significant difference between the two methods, and red when there isn't enough data. And the further you are from the dividing line, the more you have a problem. And so what we can see here is that many of the publications lie in the red area, which means that many of the published improvements are not significant and may not generalize to a new set. Okay, so maybe the problem is that we don't have properly aligned incentives and that people are just incentivized to publish and maybe not to do things right. So what we did a few years ago is that we ran a competition. The goal was to predict autism status from brain MR images. And we gave participants a public data set, and we kept a private data set. And there were incentives so that the best predictor on the private set would get some money, would get a few thousand euros. And what you can see on the figure is that some people worked very hard in the public set and got very good predictions, but these did not carry over to the private set. So this is a problem that's well known in machine learning. It's called overfitting. And what I'm showing you here is that even when you align the incentives, people sometimes do mistakes and overfit the data they have. So you can't really trust the numbers that people report. If we go beyond academia and we look at Kaggle competitions, so Kaggle is an online website where people compete to get the best predictor. And Kaggle has two leaderboards, a public one where the algorithms are evaluated during the competition. The data is not available to the participant, but the results are displayed. And a private one, which are used after the end of the competition. And so what I'm showing here in blue is the distribution of difference for one given algorithm between the public leaderboard and the private leaderboard. And as far as I'm concerned, this distribution of difference is above all sampling noise. I get two groups of data sets of the same nature. I evaluate the algorithm on one, I evaluate the algorithm on the second. It gives me two different results. This is sampling noise. So the blue distribution is sampling noise. And the red bar is the region that comprises all the 10% best algorithms. So the best one, and all the 10% of the competition that performed best. So what you can see is that on the first two plots, the first two challenges, we have the evaluation noise that is greater than the difference between the 10% best algorithm. So it means that we have improvements across the algorithms that are smaller than the evaluation noise. And on the third plot, what you can see is that there's actually a systematic shift, is that the difference between the public leaderboard and the private leaderboard is actually negative, which means that the private leaderboard performs less well than the public leaderboard, which means that the analysts once again overfit the public leaderboard and it doesn't carry over to the private leaderboard. So the point being that it's not only an academic problem. If we look at other practices, we find this again and again and again. Okay, really the root of the problem is that because of noise, we have unreliable evaluations, and the danger is that they miss the target. And one way of understanding this is to look at the sampling noise on the test set. So it depends on the size of the test set. And here I'm giving you a table that summarizes the confidence intervals of prediction accuracy depending on the size of the test set. And the fact that we have human incentives, human in the loop, means that we tend to overfit, we tend to push these things, and it actually makes things worse than what we see here. So really the challenge here is that health data in general, and in particular MR data, has small number of samples, and it leads to large validation noise and thus large error bars. So it's a fundamental problem because we have limited information in the test set. It's particularly bad when we have classification, because one image only brings a single bit of information. Other problems such as segmentation are actually much better because one image brings much more information. Okay, that was the first problem. The second problem is that we don't always answer the right question. For instance, if we're looking at diagnosing nasty conditions, this seems useful, but that's really on a case-to-case basis. Suppose that you have an algorithm that detects well cancers, but only when they're in the late stage cancer phase. That's too late to cure. That's not useful. So the questions that we take are really important. More generally, any prediction should ideally be associated to useful intervention. Elsewhere, it does not have a public health impact. Now, if we look at the publications around AI and medical imaging, what we can see is that in 2016, when the large lung challenge was ran on, so lung prediction challenge was ran on Kaggle, we can say that the number of publication studying prediction on lung cancer jumped in AI. But the number of corresponding studies in medical oncology didn't change at all. So what we can see is that our focus as a community is often more driven by data availability rather than clinical relevance. My experience is that we don't always think about how the algorithms are going to be used to improve health. Another challenge is that we would like to have meaningful metrics. By this, I mean metrics that reflect application utility. For instance, what's really important is the expected utility of a decision. The cost of misses and false detections will differ depending on the usage scenario. For instance, if I have a screening usage scenario with humans that are making second readings of detections, misses are more detrimental than false detections. On the other hand, if a detection leads directly to surgery without a complementary exam, if I have a risky surgery, then the false detections are very costly. So evaluation needs to account for how an algorithm is going to be used downstream. And for this, I need to define cost matrices, and I need to use things such as decision theory and utility. There's a fairly simple formula, actually. We typically want to have continuous predictions that evaluate the chances, the probability of an outcome. So for this, we look often at what we call calibration, which is we look at the fraction of actual detections in the y-axis as a function of the score predicted. The higher the score predicted, the higher we want the fraction of positives. And what is defined as calibration is comparing this predicted confidence to the observed error rate. Now, one thing to keep in mind is that this cannot be interpreted as an individual control on the probability of a given individual. This is an average control, and you might have subgroups on which the algorithm is overconfident or underconfident. So this is just an average control. And you need to do more sophisticated techniques than calibration to control individual probabilities. Okay, so zooming out to evaluate the usefulness of machine learning approach for health, Ideally, we would like our prediction to be associated with a useful action. We would like to use metrics that are adapted to the corresponding application scenario. And then we have one extra difficulty is that the data we have may often not reflect the application. There are many reasons for this, but really nasty ones are, for instance, the fact that it may build on consequences of the diagnostic. For instance, suppose I'm looking at diagnosing chest conditions from X-ray. I may have, for the people who have a pneumothorax, I may have a chest drain, because when people have a pneumothorax, a standard treatment for pneumothorax is a chest drain. Now, the problem is that if these images are given to a machine learning algorithm, it will learn to detect the chest drain and associate it with pneumothorax, which is completely true, but which is not useful, because if the individual already has a chest drain, it means that the diagnostic is known. So this is often the case, because often we use images to train the algorithms that are images that do not correspond to the actual application scenario. Here, those are post-diagnostic images, not pre-diagnostic images. So one problem we have is that the data often misrepresents. Technically, this is related to what's known as distribution shift. Now, there are simple cases of distribution shift. So there is the problem of covariate shift. The notion of covariate shift is the idea that X, here the images change, but the link between X and Y, the link between the image and the outcome, is preserved. So if we have a selection bias, if we, for instance, don't observe the right population, and you can see this in the jump between the figure on the top and the figure on the bottom, what you can see is that a simple model here, the straight line will fail. The straight line is the best approximation to the separation between the two the two population of points on the source data, but not on the target data, because I have a distribution shift. But if I have a flexible enough model, and I can learn it without too much noise, then it is able to carry over. So with enough data, if I just have a covariate shift, that's a benign problem. But there are settings that are more difficult. I can have selection bias that breaks association. For instance, here on the figure, I'm showing you the orange cloud of points that are a subset of the blue cloud of points. And what you can see is that in this subset, the association between X and Y is modified. And the reason this happens is because we have a common cause to the selection and to the data XY. And this distorts the association between X and Y. The important point to keep in mind is that more data or bigger models will not solve the problem here. And let me expand a couple of prototypical cases. First, there's a common paradox known sometimes as the Bergson paradox or collider bias. To give an example, the inclusion in hospitals anti-correlates pathology. Both dementia and motor disabilities lead to long stays. And so if you look at people who are staying in hospitals, the people with motor disabilities have less dementia. This is also the case in a research cohort. In particular, since polymorbid people are seldom included. So what we get in those data sets are associations that are not present in the external population, such as an anti-correlation between motor disabilities and dementia. That's an example of a collider bias. Another example I want to study a bit is when we use prediction to support decisions. So we can use sometimes prediction for decision making. Suppose we have a prognostic model that associates a health outcome to health covariates. And suppose we know that in this population, some individuals have been treated and some individuals have not been treated. So we can predict the outcome as a function of both the intervention and the health covariates, and then we can compare the two predicted outcomes, predicted for treated, predicted for non-treated, for the same individuals. And by doing the difference, we have the individual treatment effect. Now, a difficulty is that in practice, we're typically not comparing the same individuals. Typically, the healthy individuals did not receive the treatment, while the individuals more sick received the treatment. So we have a selection bias compared to balanced intervention. And the problem is that a good risk minimizer the risk is then that this a good predictor simply learns to associate treatment to negative outcomes. And so in such a setting, sometimes it's more useful to use a worse predictor. Now, I can't know what this is telling me is that I cannot know just looking at the standard prediction error. I cannot know if a given predictor is good to reason on causal effects or not. And without going into too much details, I'm not going to explain the slides. This tells me that I need to correct my prediction error. And so what I'm telling you here is that if you want to interpret predictors as in a causal way, you need to be careful and you need to use the relevant tool. So I went over common pitfalls for medical AI evaluation, the noise in the test set, the fact that we can easily ask the wrong questions, and the fact that we have the data at hand often misrepresents what we're interested in. We hear a lot about the huge benefits of AI. Those are sometimes, often, promises that have not been checked by proper measures and applications to health. This is not new. This is a promise-based economy. It doesn't mean that everything is wrong, but it means that we need to check carefully the innovations. And I'd like to say that this is a duty of academia. We need to ensure a serious conversation in the public space on what works and what doesn't, because if we don't do this, we will break the trust in science and technology. That's all for me today. Thank you.